Modern vehicles function as rolling supercomputers. They are complex systems of systems, where software defines almost every physical action. But software still needs a physical architecture to execute its commands. The boundary where silicon meets logic is called the hardware-software interface, or HSI. It is the technical contract that maps out every microchip pin, memory address, and interrupt rule. This invisible intersection is the most critical point for functional safety. If the software and hardware aren't perfectly aligned, the entire machine fails. Look at this spreadsheet stack balancing on a single chip. This is how many top-tier engineering firms still manage that life-or-death HSI boundary, through thousands of rows of manually emailed data. The flaw is that these are static, disconnected documents. They cannot keep pace with a high-density, rapidly changing engineering environment. If a hardware engineer updates a memory address, but the software team doesn't catch the notification, the two sides of the system drift apart. The result is software written for a phantom register that no longer exists. This disconnect leads to sudden system crashes during testing and massive debugging costs late in the development cycle. To prevent these hazards, engineers need an unbroken digital thread that keeps the hardware and software locked in a single shared reality. That thread is provided by SysML version 2, introducing a framework known as System as Code. Instead of just drawing pictures, SysML v2 operates on a foundation called KerML. This revolutionary foundation allows engineers to treat the physical architecture of a machine as precise, mathematically calculable data. Engineers now define architectures using textual notation. They interact with physical specifications exactly as a programmer interacts with source code. Because the architecture is now written as code, the entire blueprint can be version controlled. Every change is tracked, and every team sees the same updated record at the exact same time. This approach uses a definition versus usage rule. An engineer writes the rules for a hardware component once, and then uses that definition across the system, ensuring identical properties every time. It also solves the problem of port compatibility, ensuring data flowing out of hardware is exactly what software expects to receive. Here are hardware out and software in ports lacking connection logic. By adding a simple tilde symbol to the software code, the model acts as a mirror, automatically reversing the port direction to guarantee a perfect match. The system also enforces physical units. If one part specifies milliseconds and another uses microseconds, the model flags the mismatch instantly. These features transform subjective human descriptions into a precise, logical structure that the system can automatically verify and execute. In automotive engineering, safety is managed through the ISO26262 standard and its ASIL hazard ratings. Imagine a low-security infotainment module sending a command to a high-security steering register. SysML v2's reasoning engines evaluate the safety constraint instantly. Catching the mismatch, a digital gate blocks the connection and triggers a model build failure with an explanatory error log. This shifts left the entire engineering process, identifying fatal integration errors before any software is written. Once the model passes these safety checks, it serves as the single source of truth for the entire project. Because the model is structured as code, it has a built-in REST API. This allows other tools to pull the verified specifications automatically. The API extracts the data and formats it into a JSON tree, a machine-readable format. This tree feeds into an automated code generator, removing manual translation. The generator instantly outputs perfect C language headers and XML files for the software teams. This pipeline ensures that human translation errors are removed from the process of turning a design into a machine. Consider the impact on a real workflow. If a hardware designer changes a single pin layout in the source model and commits that change cascades through the entire pipeline. It is validated, extracted, and regenerated into new software code in a matter of seconds. By adopting this framework, engineering is eliminating the friction between hardware and software, ensuring tomorrow's machines are built on a verified digital record rather than fragmented documents.